Hi, and welcome to Allen High School. This is a course for AP and IBHL1 chemistry. Right now we're going to be focusing on combustion reactions, a little bit more straightforward than some of them that we've done. It's pretty much some memorization and balancing, and that's it. Now, based on my previous experience with my last few videos, maybe I need to be offering candy bars for those who find my major boo-boos. So keep your eyes open. Now, how do we recognize a combustion? Now, one thing you have to remember is you are not in pre-AP chemistry anymore. There's one boo-boo right there. There's no subscript there. But in pre-AP chemistry, all we did was hydrocarbons when we talked about combustion. And when you combust hydrocarbons completely, you do get CO2 and water. Now, we're going to be dealing with other substances. And I've had students take substances that have no hint of carbon nor hydrogen and still write CO2 and water as products. And so we want to be avoiding that type of thing. Really, any reaction in which we are adding oxygen to form a compound or oxygen to a compound or really an element is going to be a combustion. So we end up having a little bit of an overlap. Technically speaking, if you took magnesium and burned magnesium in the presence of oxygen, which we all know is tons of fun, to get magnesium oxide, that's technically a combustion. But we also call that a synthesis. So there's overlap when we categorize, and that's fine. The key is being able to come up with enough of a category that it gives you direction for the products. Now, we'll be looking for oxygen, but here's the issue, that you're going to see words like burned or combusted, but you have to include the oxygen. Very often, the oxygen's not going to be explicitly supplied as a reactant. So this is one of the few times that you will have to know to add a reactant in order to work the problem. Now, there's some general guidelines. This was basically what we saw in pre-AP chemistry, was forming CO2 and excess oxygen. That's often called, especially when it's with a hydrocarbon, complete combustion. And IB, I know I have seen this distinction numerous times in problems. If it's carbon monoxide, then it's called incomplete combustion often. Now, if the problem specifies that we are dealing with either limited or excess oxygen, then you will need to supply a particular product. If it says limited, you need to put CO2. If it says excess, you need to put excess. But if those words are not given, then you assume CO2. Okay, so that's your most common. And remember, AP often accepts a whole variety of answers. We're trying to get at the most common or the most likely. Now, for SO2 and for sulfur, I want you to remember a long time I indicated that carbon and sulfur and SO2 and CO2 tend to behave very similarly. And yes, the SO2 is in the limited oxygen here, but it's also the most common. It's the one you will assume. If it says excess, then you'll put SO3. Nitrogen is NO2 limited, limited, NO2 excess. We assume the NO2. Now, phosphorus and sulfur are a little different. You notice here I put S8 and not just S. Sulfur exists in a little covalently bonded ring. This is the common sulfur. It's going to be a yellow sulfur. It's going to smell like matches if you burn it. And it's a little covalent ring of 8. Now, the most common phosphorus is white phosphorus. There's also red phosphorus that's more of kind of a polymer of this, is what I was reading in, where else, Wikipedia. And this is, I wanted to get you a picture of the phosphorus. Do you see that it's bonded together in tetrahedral arrangement? Okay? And then if hydrogen's present, it makes H2O. If a metal's present, it makes the metallic oxide. So let's move forward and try a couple of these. Now, most of the ones you're going to see in your homework that we'll be working on in class will be organic. And for a while now, you're going to need to look up the formula. I'm trying to find a day to squeeze in organic formulas and naming, and I think it's going to be at the end of this semester. But until then, just look it up. Just do a quick Google of octane. Actually, you should know octane from pre-AP. This was one we did where it was CN, H2N plus 2. So if I double that plus 2, I'd get 18. We are burning, and this time it did say excess oxygen. And so we know we had oxygen. And since it's excess, we're going to form CO2 plus H2O. Now we need to balance. So I like to save my oxygens for last. I have 8 carbons, so I need an 8. I have 18 hydrogens, so I need a 9. Now that gives me 16 plus 9 oxygens, which is 25 oxygens. Well, you're not going to get 25 oxygens out of O2. And you will see times when halves are used to balance a diatomic. But the AP instructions explicitly and clearly say lowest whole number ratios. So when you have an even odd issue like this, we can always make an odd number even by multiplying by 2. So this is a 1. I'm going to multiply it by 2. I'm going to multiply this by 2. I'm going to multiply that by 2. Now, if you recount your oxygens, you'll see we should have 50. So this becomes a 25 in front. So that's pretty much it. There's no spectator ions or anything like that. Now, this asks us as a question. I wanted to go ahead and start introducing some topics to draw an isomer of octane. Iso means same. Isomer is same molecular formula, but different structural formula. Now, I'm going to take the easy way out and just draw lines to represent my hydrogens. Now, this does not have a functional group like an OH or a BR or something like this. So I think the easiest thing to do when you're doing these, because there's many isomers of octane, I like to simply erase an end. Okay, we can erase 2, no big deal there, and move them to the middle. And then put in our hydrogens. And put a red one there so you can see it there against the white. Now that still has 1, 2, 3, 4, 5, 6, 7, 8 carbons. And if you count, it still has 18 hydrogens, but it's a different structure, completely different structure. Now you can't just bend up the end. You truly have to move the end into a middle someplace. And you can do them first 1 at a time and then 2 at a time, and so on and so forth. So I just wanted to go ahead and introduce that concept to you early on. Now let's take a look at the next one. Propane is burned, but notice the key term here. It says in limited oxygen. So we have propane. Prop is 3 carbons. I don't know if you remember this, but meth eats people's brains is what one of my students came up with a few years ago. We used to say mom eats peanut butter. Meth is 1 carbon. Ethyl or eth is 2 carbons. Prop is 3 carbons. Bute is 4 carbons. So I have 3 carbons. It's an ane, so I'm going to double it plus 2. I'm going to add oxygen. Now it says that I have limited. You really need to know that that makes carbon monoxide, and that's poisonous, and it binds to our heme group. So that could have been a question here. I kind of doubt it, but I'm trying to stretch to help you learn anything I can within that concept. And then I'm still going to get H2O, regardless of whether it's limited or not. Now we have to balance. I have a 3 here, so I'm going to put a 3 here. I have an 8 here, so a 4 here. That gives me 8 plus 3, which is 11 oxygens. So we're right back with that even-odd issue. So what do? We double all coefficients. That was a 1, it becomes a 2. That was a 3, it becomes a 6. My 4 becomes an 8. Recount your oxygens. I have 6 plus 8. So let's make sure I didn't miscount here. Okay, so I've got 8 here and I've got 6. That's equal to 14, which is not quite making sense to me, but maybe I miscounted in the first place. 16. Okay, we're just going to run with it, and that's a 7. So let me double check, because something doesn't look quite right to me, but let me double check and we'll make sure that we had that. So we had H2O, and we had CO, carbon monoxide. This gives me 6 carbons. This gives me 6 carbons. This gives me 16 hydrogens. 8 times 2 is 16 hydrogens. And this gives me 14 oxygens. And 6 plus 8 is also 14. So that looks pretty balanced to me. And I'm sure I will hear about it if I've messed up. Okay, sulfur is burned in the presence of excess oxygen. So we've got S8 plus O2. And that's going to give me SO3. And I have to balance that. So I've got 8 sulfurs here, that little cluster, funky cluster. So I'm going to put an 8 there. That gives me 24 oxygens, and so I will need a 12 right here. Now, this asks about an environmental concern, and you would think we could think about global warming, and that certainly is a possibility, but more often or not, when I see an environmental concern on an AP question, I have seen acid rain as the answer. And in this case, we will be learning. So for now, you just have to memorize that metal oxides in the presence of water, non-metal oxides, in the presence of water make acids. So that's going to make H2SO4, which would be acid rain. Honestly, H2SO3 from sulfur dioxide would be more common, as are some of the nitrogen-containing acids. Okay? Now, I realized I didn't quite finish this problem. I didn't answer the question since I'd messed up my balancing. It asks for the molecular structural name around each carbon. So I want to go ahead and do that so we can start integrating our knowledge better. Now, do you notice here that each carbon has an AB4 structure? An AB4 structure we'll be learning is tetrahedral. Okay, and it's been a while since we've done that. So that's certainly not going to be tested anytime soon, but we want to start seeing how we're going to integrate all of our knowledge. Plus, we did this way back in the olden days, 2 years for some of you, which is ages ago, and so much knowledge ago that it fell out of your brains that an AB4 structure was a tetrahedron. So let's go on. One more, and I think we can finish it all in one video so that you have not too much to do. And let's take a look at our last one. I did make this up, so hopefully it's realistic. So we're just going to follow the rules, even if it might not quite happen, at least safely. So the rules tell us that when oxygen goes with sulfur, since it's not indicating limited or excess, I'm going to use the most common SO2. And then the rules also tell us that when metals go with oxygen, they make the metal oxide, so Na2O. And then we would have to balance this puppy. There's no dissociation, nothing like that. So I have 2 here and 2 here. So I'm going to have to put, the sodium's fine, but I have 2 oxygens and 3 oxygens and a sulfur. I can tell right off the bat this one's going to be a tough one. So I'm going to put a 2 there, but then that gives me 4 here, so I'm going to put a 2 there. Now my sodiums are balanced. but my sulfurs aren't, so I have to put a 2 there. Now I have 4 plus 2 equals 6 oxygens, so I need a 3. It's never a bad idea to double check that that's the lowest whole number ratio, and it is. So that's it. We'll be working on combustion in class. I bet you get it all done, that it's so straightforward, maybe except a little help with the questions. Until then, this is signing off.